Imagine I have a charge q which is moving from left to right. Now this charge moving from left to right is equivalent to a small localized current, call it I, going from left to right, and therefore it will create some magnetic field surrounding this line of motion. So I can draw those magnetic field lines using this strip of paper here. Those magnetic fields will be circular, like this, like this, like this, 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 and here it's like this. Okay, so those magnetic field lines are circulating this line of motion, and they look like this. Now if I want to indicate these flux lines in 2D in this plane of paper, an elegant way of doing that is using this symbol of dot and cross. Dot means lines of force coming out of the paper, cross means it is entering the paper. Okay, and on this side, everywhere the lines of force will be coming out of the paper like this, and on this side it will be entering the paper like this, and as you can also imagine that the field nearer to this charged particle will be stronger, and therefore I am indicating them with larger cross and dots, and as I go further away and away from this this charged particle, they will be weaker, therefore I am drawing them with smaller dots and cross. And the direction, as I already indicated, here on this side, upper side is all coming out of the paper, and on the lower side all going into the paper. Okay. Similarly, if the charge is now moving in any other direction like this from here to here, then the magnetic field distribution will be like this. On my right side, the magnetic field will be entering the paper, and on my left side the magnetic field will be coming out of the paper. Now with this in mind, let us consider a thought experiment. Here I have my x-axis, and here I have my y-axis. I will take two charged particles q here and another one q here. Let me call this as q1 and q2. But q1 and q2 are same, equal. So I write that q1 is equal to q2. Identical charge particle. And this is moving towards the right. Call this speed v1. v1 is the speed, and here the speed of this particle is v2. So this particle is also moving along the y-axis. And I choose that V1 is equal to V2 in magnitude. Okay, their direction is different. So if V1, this V1 vector is towards the right, this V2 vector is towards the y-axis, but their magnitudes are same. This is what I choose. Okay. Now, while this is moving and also this is moving, they will repel each other due to Coulombic repulsion, because both of them are charged and similarly charged. So therefore, they will repel each other along the line joining them, and therefore here I will have a Coulombic repulsion which I call as Fe acting along this line joining these two particles, and here also the Coulombic repulsion will be Fe, okay, or I call it Fe1 and Fe2. But of course, the magnitude of Fe1 will be same as the magnitude of Fe2, because that's what Coulomb's law says. These two charged particles will repel each other with the same force, equal in magnitude but opposite in direction. But at this moment there will be other forces also acting on these two charged particles. Not only this Coulombic repulsion, there will also be some magnetic forces, electromagnetic force, Lorentz force. Why? Because when this charged particle is moving, it will create its magnetic field surrounding it. And that magnetic field, okay, so that magnetic field will look somewhat like this. If I bring it here, you can imagine this is how will the magnetic field be created by this charged particle. And so therefore, everywhere on this upper half, the magnetic field will be coming out from the plane of paper, here it's stronger, here it's weaker, because this point is farther from this charge. Okay, but everywhere it is coming out from the plane of paper on this side, on the upper side, and on the lower side it is entering the plane of paper. Here, everywhere it's entering on this lower side. Now this second charged particle Q2 is in the magnetic field created by the first charged particle. Let me call this magnetic field B1. Why 1? Because this is created by particle 1. So this B1 created by particle 1 will give some force on this moving Q2, and this force is governed by the Lorentz formula, which is F is equal to QV cross B. So this is the formula or the rule of for the force acting on a moving charged particle in a magnetic field. So here on this particle we will have some magnetic force, electromagnetic force, And let us first find the direction of that force. B here is coming out and V is along the y-axis. So V cross B, so if you calculate this cross product, V cross B will be along the right side. This is the direction of the force. I call it Fm, okay, because this is created by this magnetic field. Similarly, when this charged particle is moving, it will also create some magnetic field. And how will that look like? That will look like this, So on my right side, the magnetic field will be entering the paper, and on my left side, the magnetic field is coming out of the paper. So on the right side, I will have magnetic field entering the paper, here quite strong, here bit weaker, here also bit weaker, more weak, but it's entering the paper. And on my left side, the field will be coming out of the paper. Okay, so let me call this B2. Why B2? Because it is created by particle 2. And this is the value of magnetic field near particle 1 created by particle 2. Now particle 1 is in the magnetic field of particle 2. Therefore, on this there will be some Lorentz force. And how much will be that force? That is once again governed by this equation, F equal to Q V cross B. What will be the direction of that force? Let's find that out. Now V is towards the right, B is downwards entering the paper. So if you take the cross product, you will find the force will be upwards. Let me call this Fm1, and the previous one I call that Fm2. Fm2 and this is Fm1. I can easily see that Fm1, magnitude of Fm1 is same as the magnitude of Fm2. Why? Because the magnitude of B1 will be same as the magnitude of B2. This is B2, this is B1. I can easily say that magnitude of B1 is same as the magnitude of B2. Why that is so? Because these two charged particles have same charge, same velocity, they are at same distance from the origin in a symmetric manner. So therefore the magnitude of the magnetic field B1 created by Q1 should also be same as the magnitude of B2 created by Q2. And therefore B2, the cross product of V1 and B2, so V1 cross B2 should also be same in magnitude with V2 cross B1. So therefore if M1 and if M2, they should also be same. So what do we see here? We see that these two magnetic forces are same in magnitude but not in opposite directions. That there is something wrong. Why? Because now if we calculate the total force acting on particle Q2, that will be a vector sum of Fe2 and Fm2, which you can calculate by taking the parallelogram law into account. So this will be the direction of net force. Okay, call it F net 1, F net 2, which is in this direction, and here on this particle net force you can find using parallelogram rule. It will be in this direction, F net 1. Something is definitely not very satisfying, because the force on particle 2 and particle 1, they are not in opposite direction. So particle F net 2 and F net 1, they will be equal in magnitude. Their magnitude will be same, because Fm1 and Fm2 are same in magnitude, Fe2 and Fe1 same in magnitude. The entire situation is symmetric in according to the diagram and the description. So it's obvious that F net 1 and F net 2 are same in magnitude, but they are not same, they are not opposite in direction. Is it possible? Is it allowed? It seems like violating Newton's third law. How is that possible? Did I do any mistake in my calculation? Maybe, most likely, I guess. Otherwise there is something definitely wrong in the physics that I have learned so far, because then either Newton's third law is not obeyed, or maybe then Lorentz force formula is wrong. But I know both this Lorentz force equation and Newton's third law is true. Then did I do any mistake while analyzing this thought experiment? It is your I request you, please see if I did any mistake, and please tell me what is wrong here, please.